What the Webb telescope is capable of, we already understood from the first images made public on July 12, 2022. But especially from the concerned faces of cosmologists when they learned of the unexpected discoveries of already well-formed galaxies at a time when, according to current theories, there were hardly even supposed to be stars. James Webb, in short, in not even a month of scientific activity, is already revolutionizing cosmology. But of course, speaking for scholars and enthusiasts alike, what we expect most from this marvelous machine is the answer to the question that most of all disturbs the sleep of us, the inhabitants of a planet scattered and lonely among the depths of the cosmos. Are we alone? Is our Earth the only island overflowing with life? Could it be that all the billions of other planets scattered in the Milky Way are just matter? Webb is not really an exoplanet hunter. The Kepler Space Telescope was. But with its 6.5-meter diameter primary mirror and infrared spectroscopy instruments, it is perfectly suited to peer into these distant worlds more closely than ever before, telling us what they are made of and, potentially, whether there are signs of life in their atmosphere. So, draw close, for together we shall peer into the universe and see if anything looks back. Larger and larger radio telescopes, entire decades spent scouring the sky for a signal, millions of electromagnetic frequencies explored, and nothing. Not even the faintest hint of life outside our Earth. Instead, the SETI search, which half a century ago seemed to start with the ambition of being able to find intelligent life within a few years, has gradually stalled, hampered by funding problems, but even more so by the statistical improbability of its mission. But even with the dream of Frank Drake and Carl Sagan gradually waning, the possibility of achieving the same result by another means began to take shape at the end of the last century. Investigated from Earth and then from space, the stars closest to our solar system indeed began to reveal that they too possessed planetary systems. The first of the exoplanets to be discovered, you may recall, was the now mythical 51 Pegasi b in 1995. Today we know of more than 5,100 of them, a boundless archive that has been gradually enriched mainly thanks to the Kepler Space Observatory, a diverse set of specimens ranging from Earth-like rocky planets to Jupiter-like gas giants, and even planets very different from those in our solar system. For example, super-Earths, rocky planets far more massive than Earth. An enormously important database, but one that for many years only served to stir our imagination. What to do with this information? By what means would we ever come to know anything more about these planets that, in the vast majority of cases, had not been directly observed, but only derived from numeric analysis of transits on the disk of their parent star? It was like having a vinyl record without the gramophone capable of playing it. Yet in parallel with the increasing amount of data available, the technology that would one day be able to use it was also being refined. Indeed, plans were beginning to be drawn up for the 30-meter class of very large diameter telescopes, such as the 39-meter Extremely Large Telescope, capable with their high-resolution spectrographs of easily finding elements such as gaseous oxygen in the atmosphere of an Earth-like exoplanet. Most importantly, the long-sought heir to Hubble, the 6.5-meter James Webb Infrared Space Telescope, was in the advanced stages of design. Unfortunately, for a variety of reasons, neither the Extremely Large Telescope nor other super instruments such as the Giant Magellan Telescope or the 30-meter telescope are currently operational yet. They certainly will be before the end of this decade, but this means that, to date, we can only count on the extraordinary performance that the Webb telescope, which has now been at work for a couple of months at 1.5 million kilometers from Earth at the Lagrangian L2 point, will be able to offer us. But what can we expect from the Webb telescope? We certainly should not expect beautiful images of exoplanets. Webb is a large and powerful instrument, and it can see billions of years into the past. But resolving an exoplanet in a way that resembles the planetary images taken by Hubble or Voyager is still far beyond its powers. It is true that in some cases, Webb will make actual photographic shots of exoplanets, but even the larger ones will only appear as a bright spot. Before proceeding, be sure to leave a like for the algorithm and subscribe to our channel clicking the bell. This will encourage us to do better and you'll never miss any of our weekly videos. In fact, a portion of Webb's early observations will produce direct images, obtained by blocking the light from the host star with a coronagraph. Most of these observations will involve large planets, gas giants, and perhaps icy giants that are located far away from their stars and are therefore easier to detect once the star's light has been erased. Besides, Webb will be able to do better than that. It will be able to let us know whether the atmosphere surrounding a planet possesses the characteristics necessary for the occurrence of life. And this will be accomplished mainly by the transit method. That is, by following the planet as it passes over the disk of the parent star. In this approach, the star's light will back-illuminate the gaseous envelope encircling the planet, bringing new spectral lines to Webb's spectrograph that will reveal whether or not important elements are present in the atmosphere. This method can be used to recognize the presence of certain atmospheric gases associated with life, such as oxygen or methane, because these gases leave very specific marks in the light. It can also be used to detect particular colors on the surface of a planet. On Earth, for example, pigments used by plants and algae for photosynthesis capture specific wavelengths of light. These pigments produce characteristic colors that can be detected using a sensitive infrared camera. If you were to see this color reflected off the surface of a distant planet, it would potentially signify the presence of chlorophyll. Understanding what a planet's atmosphere looks like is one of the crucial ingredients in determining its climate conditions and actual propensity to host living organisms. Not only that, but the very presence of life can measurably alter the composition of the atmosphere, as was the case on our planet with the appearance of photosynthetic organisms, which released enormous amounts of oxygen. Moreover, the relationship between chemistry and life is not always so direct, and even the possible discovery of biological relevant molecules would still require careful interpretation. Compounds of clear biological origin can also be generated by geological processes, and thus the detection of methane, to take an example recently debated regarding the atmosphere of Mars, would not necessarily stand for the presence of some form of life capable of producing it. The detection of these false positives will therefore represent a critical step in the search for traces of some form of biological presence, but will not allow absolute certainty to their discovery. This search for habitable exoplanets is already underway, with Webb's first reading in June 2022 of the giant exoplanet Wasp 96b. Located about 1,150 light-years away in the southern constellation Phoenix, it represents a type of gas giant that has no direct analogues in our solar system. With a mass less than half that of Jupiter and a diameter 1.2 times larger, Wasp 96b is in fact much more puffy than any planet orbiting our Sun. And with a temperature above 700 degrees Celsius, it is significantly hotter. Wasp 96b orbits extremely close to its Sun-like star, only 1/9 the distance between Mercury and the Sun, completing one revolution in just 3.5 Earth days. And it was the favorable combination of its large size, short orbital period, and very large atmosphere that made Wasp 96b an ideal target for Webb's very first atmospheric observation. Thus, on June 21, 2022, Webb's near-infrared imager and slitless spectrograph measured light from the Wasp 96 system for 6.4 hours as the planet transited the star's disk. The result was a light curve that confirmed properties of the planet that had already been determined by other observations, while the spectrum revealed the unambiguous signature of water and carbon dioxide, indications of haze, and evidence of the presence of clouds that were thought not to exist based on previous observations. Not bad at all for a first observation made more for demonstration purposes than anything else. In the coming weeks, however, things will begin to get serious, and Webb will turn its mirror towards Trappist 1, a cool dwarf star located 39 light-years away in Aquarius. This star became quite famous in 2015 when it was discovered to host a procession of 7 rocky, Earth-like planets, 3 of which would orbit in its habitable range. In particular, estimates from the Planetary Habitability Laboratory at the University of Puerto Rico in Arecibo indicate for the planet Trappist 1d an Earth-like index of 0.90, the highest among extrasolar planets at the time of discovery. And it is really exciting to think that before long, the Webb telescope may be able to tell us whether we can consider these planets as other Earths. That perhaps one day we will reach with technologies that do not yet exist but are ready to be developed, just as it has always been the case in our history, one step at a time, as we continue to ascend to the heavens.